morning. I hope I'm audible and back. Yeah. So I shall talk about a very generic overview of AI and not really addressing the concerns or the problems of power systems per se, because I thought that it's important for all of us to get an idea of the overall canvas of AI. Because even when we do research, we look at a very narrow window in which we are focused on. So I've chosen the topic, the state of the art of AI and its advancements. I shall try to go through it very quickly to give an overview. And this is my organization of the talk. So if you see, this is definition of artificial intelligence. If you look at in a formal sense, so AI has all the characteristics of general purpose technology. I think this is something very, very important. Therefore, it can be used in a variety of fields. And if you see today, there is no field which is not getting affected by AI. Even yesterday, I was in a seminar in Delhi, which was organized by Humanities Department, who were talking about AI in the space of humanities and how it is impacting. So there is no area of human learning which is not getting impacted. And if you see today that as we have talked about even applications, computer vision, natural language processing, and machine learning and expert system, robotic systems, these are all actually is part of our usage in various industrial problems. So let's look into this evolution in search. If you go back to the starting point of AI, and in fact, when AI was also coming up, even during our possibly undergrad days, it was problem solving where the AI was focusing on. Even today, it's focusing on problem solving. And that time, there was this concept of state space, and by problem solving is actually search in that state space, because problem solving means what? Conditions of choice of parameters and conditions to enable the system to do a task. And I have to search in that space to get an optimal solution to make the system task in a proper way. Therefore, it is kind of a searching for solution. Even today also we are searching for solution. Even what we are doing in AI is fundamentally problem solving and a goal-directed search. Goal-directed search is giving rise to different techniques and technologies that we use. So classically, this is an example of a goal-directed search where these are all states, and we have to actually rearrange the numbers, and I can do a search in that space of states. And even when we machine learning, we also search in the space of parameters. Parameters are continuous, so my search space becomes now a differentiable problem, not in this case when it is purely symbolic. If you see that first AI came in with games, with chess, and if you see that the AlphaGo, that was also a landmark event, these are all actually based on classical state space search. And today's even games, which our kids play, or we also sometimes play, definitely the younger colleagues must have played that in a live. And these NPCs, not core characters, okay, they are all actually respond with AI and AI built into them. So now all of this involves actually planning and action. And what AI's original vision was that there will be actors which will take action and which we have to implement. So therefore, if you see, the abstracted vision of AI is, if you look into this, that there's an actor does planning, and on the basis of planning, it acts, and therefore plan generates acting, and acting is actually generates query, and it receives input from other actors, which may be visual sensors, this can be other objectives, messages, and it executes. Therefore, the percepts are coming from the signals, and commands are going and changing the external world. And this is the communication thing, because interface with the other systems which would like to use the actor for a purpose. Now, when we talk about machine learning, we talk about today's machine learning based systems, etc., we tend to forget about this model of actor. But today we are coming back to there, because actors actually are instrumental to address any of the engineering problems. So today, see, this is an example. You can look at this site that where the entire supply chain is being managed by an actor and actor-based implementations. So everybody talks about machine learning. So evolution of machine learning models, if you see number of models which has come through, and today everybody talks about deep learning models, and it started and made huge impact with convolutional neural networks, and ImageNet has been the perfect example where it could recognize a large number of objects. Before that, no other system could do it. And there is recurrent networks, but today's state of the art is not this deep learning. And this is also something very, very important we should be clear about. And in fact, there has been also a huge change in the way the learning happens. We used to talk about, I shall come to the other the issues that different training techniques which are used. See, we classically talked about supervised, unsupervised, but today there has been much extension into it, and we see what can be done. Now, therefore, with AI growth, the AI umbrella that I'm talking about is actually, if you see computer vision, today we have talked about computer vision being used in asset management, and there are a number of various areas in terms of grid, even power line protection, even that I think IIT Kanpur professor will talk about that whole inspection system, and the other sensory perceptions. All of these, including robotics, virtual reality, and all of this together, when you talk about Industry 4.0, a completely automated production line, even for power. But if you see today, we are coming back from 4.0 to 5.0, where we are not just using only AI or robo, but we are also recognizing presence of human in the whole pipeline. And this is something also very, very critical for us in a country like India, where we really have the human resource, and how AI can help exploit the human resource more productively and more profitably. That's also the challenge for all of us. So let's go back to machine learning that we was talking about, and classical machine learning uses what is called discriminative modeling. All predictive maintenance that we talk about uses predictions. Even in terms of audit, when we talk about finding out anomalies in the audit, these are all based on, many of those are based on what is called discriminative learning, where we know what is one class distinct from the other class. And the prediction is actually, given the data, can we predict to which class it would belong to, maybe today or maybe in future, if you take explicitly the time into account. So that's the classical discriminative model, and convolutional networks, deep reinforcement learning, recurrent networks, all are examples of these discriminative models. What is reinforcement learning? There are two different things that we should talk about: supervised learning and reinforcement learning in that terms. So this is first is supervised learning. We know supervised learning, I know what fault to be detected. If I know what fault to be detected, I can train a system to detect that fault. That's a supervised learning. And that's actually a discriminative model, because it does this separation between faulty elements and unfaulty elements, non-faulty elements. But here we shall come back to this when we talk about reinforcement learning. In reinforcement learning, I do not know what is correct or wrong. Look at a child. If there is a candle with a light, a child gets attracted to it. It moves towards that. But when the child comes closer to the flame, realizes it's painful. Okay? The pain prevents the child from coming back and trying to do that task. So it's a reward come penalty. He was trying to do something and got a penalty, is not coming back. So I do not know the exact class level, but I know the reward and penalty difference. Okay. So unsupervised learning is, I do not know the levels, but I know I have the data. I need to differentiate the data between the classes. So therefore, if we talk about the data, these are actually, I want to see that what is the lower dimension, because I have huge volume of data. If I actually make a measurement at a given point of time, all the parameters of a power system operations, it may have more than 500 parameters. But if I want to do some kind of an analysis, we need not work with 500 parameters. We need to go down to a lower dimension. In fact, unsupervised learning is one way to bring down things to a lower dimension, and autoencoders, etc., that we talk about today. But what is very, very critical is that unsupervised learning is also, if you see, can estimate underlying probability density of something which is there. So now go back to this diagram. If I know how to distinguish between these two groups, I actually know the probability distribution with which these two data sets are distributed. And when I use supervised learning, since I have the label samples, I do understand or infer the distributions. The interesting feature is I do not know the form of the distribution. I do not know whether it's Gaussian. I do not know whether it is any of the other forms, but I know functionally I have a model of the distribution. But when it is unsupervised learning, I also can infer the distribution because I've got the data, and just by looking at the nature of the data, I can discover the distribution. So therefore, this leads us to an area what is called generative AI. And everybody is today, the large language models, etc., that we talk about are examples of generative AI. So when you discriminate, I know the two classes of data belong to two different classes, and I have learned the class boundary. What is generative AI? Using unsupervised learning in principle, I learn the distribution of given data. So if I pick up pictures of Da Vinci, okay, paintings of Da Vinci, or some artists for that matter, I pick up the pictures, the paintings. And the paintings, if I just do our unsupervised learning with the paintings, the pixel colors or the other features of those paintings actually give rise to a distribution which represent the style of that artist. Now, AI provides a mechanism to generate a sample from that distribution. And that's exactly your generative AI. So you see today, so many fake paintings are there on the net. Okay, because with the data that is available already, I have generated the distribution. Then I've got the tool and tricks to pick those things up and create new examples. And that's the science of fake in that way. But also that has an advantage of as you do the natural language processing and query answering on your large language models. But to go to the large language models, what has importantly has happened is we have come across a new model which is called transformers. Transformers are substantial advancements over the deep learning models like your CNNs, RNNs, etc. In fact, it's a distinct improvement upon a form of RNN which is called LSTM. So essentially we come to transformers. So transformers therefore transform a set of input to some representation state into corresponding set of data vectors in some other new space. That means one space to another space. So if you look at in a very intuitively, I can go from say text to image. Okay, and now transformers can enable that thing to happen. Okay, that's why it's actually much more advanced compared to your deep learning techniques that we talk about. And it uses another very interesting thing which is called attention. That concept was not there earlier at all. We talk about attention. When we are looking at a picture or we are looking at anywhere, you are giving attention to some words. I have used this color to draw your attention. So that is enabling you to interpret the thing with your focus on that sentence. Now, can I do that? Because that's an element or exposition of your intelligence to know where and how to put attention. Can I build that into machine learning systems? That was a major innovation which happened around 2017-18, which is called attentional models. And transformers with attentional models have changed today the space of AI. It is completely different today. And it can therefore, if you see that using that. This is called LLM era. And what is happening in LLM era? Don't get into the boxes, but what is interesting is I learn representation. Okay. So if you see an input, if I give enough of English sentences, I would learn the syntax, grammar, and semantics of English text. And this is what? This is a decoder. What is the significance of decoder? Decoder also have input. Decoder is actually the generator. And given English, I actually do the, I know how to, what is English, how to interpret, create a computer model for English and English generation. But in the decoder, if I give input French and have an attentional, cross-attentional model between English and French learned using encoder, decoder together, then I get an automatic translator. So it is not just I am learning something, I am learning to produce something given the external input. This is the power of AI today. It's not that I am able to discriminate. I am able to say this fault, this is a fault and not correctly it's working. But I have also the ability to generate what could be the other faults as well. I think that's actually the whole challenge that this generative AI is meeting and transforming all our perceptions and the ways we deal with this problem of predictive maintenance, reliability analysis, etc., etc. So this also brings in another very interesting new model of learning, which is called self-supervised learning. In fact, we talk about labeled data. We actually, at one point of time, there was an industry in India where people with very low level of educations were appointed for labeling data and providing that labeled data to many of these multinationals for building their learning models. But today with self-supervised learning, that labeling itself requirement has disappeared. So the whole modality of learning has actually changed. And that is brought in by this what is called masked span prediction. That it's something like that, I want to know how a sentence is formed. So I just mask a part of the sentence and then try to predict that part from the part of the sentence which is before that phrase and after that phrase. And based on predictions on both the sides, I learn what should be really the sentence. So I don't need any labeling at all. By doing just masking, I learn, and that's how all of these these LLMs have learned the data. Because it is impossible, you can realize that I cannot have labeled data over the entire internet domain. It cannot be labeled. It's only partially labeled, it's only self-supervised. So therefore, it is also task. I can train for multiple tasks one system. Today's, if you see, look at your classical supervised learning model, it is a learning only one task, but I can learn multiple tasks. And that's exactly what is interesting. And if you see, it says that every task, including translation, question answering, etc., can be learned by specifying the task itself in natural language. And once we know this is again, it's a LLM inference prompting. I think all of us know what is prompting based task, because once I know for a set of tasks, then I can ask the LLM to do a task by giving a query. And I can train LLM with given set of query to provide answer to me. So OpenAI has done the model, but I need not have that model per se. That model can be running on internet, but I can train that model for my purpose. But in that process, what is happening? You have to also realize that your queries, your requirements, the data you are putting for generating some output is also becoming property of OpenAI. This is also a very important challenge in terms of our data protection. That is, by using LLM online for a task, we also at the same time risking our data to be leaked globally and for other players. In fact, this is also a very interesting thing which goes up in terms of generating the data for that purpose. See, reinforcement learning in this case is actually, if you see, can be used for improving these LLMs, because you actually provide the input you are becoming the source for learning because you are telling whether it's correct or wrong. And that's how the LLMs and others are picking up and learning. And then what is coming today is multimodal, because if you see, LLMs first of all do make errors, do make hallucinations. Okay, why? I shall just come to that point why, but it's also important that LLMs don't know that red is a color and what is the semantics of red as a color. Because red is a word, it just knows the word. The semantics of red for us is because we have eyes. Visually we know what is red and we can associate red with the concept of the word red. So until unless I have the grounding, none of the semantic analysis is valid. This is the biggest challenge of today's LLMs, and that's why people are moving into multimodal LLMs, where actually use language as a basis, but on the basis of the language, you try to interpret other mediums, and together actually make things much more reliable. In fact, there's been a number of problems. In fact, if you see today, your radar signal processing is happening through a kind of multimodal systems. Then comes, we are going back to the actor. I started with actor. Today's state-of-the-art AI, we talk about agentic AI. The agents, so all these algorithms put together can give me agents. Agents can perceive, reason, act, and learn. So it can perceive if it's using vision, it can perceive while you're talking to it, and based on that, it can act and produce results. So if you see today, the movement of AI, where it has gone, if you look at, we were here, process automation. From there, we have supervised AI, ML, generative AI, and this is what is agentic AI. If you see, this is the old picture that starts with of an actor being deployed for tasks to be solved. And this is an example. Using this high-level language at the core, this is the agent response. So it could be, you see that Amazon, your interaction and Amazon can be completely captured by an agent. You don't need to search or do anything. You just say that I want to buy a shoe. Based on your history of what you have bought in the past, it will search on the internet, look for the size, look for the match, make some conclusions and give it to you until the shoes is arriving next week. So it is acting. See, learning was not really acting. Acting part was with the human being. When we are getting into agentic model, AI is also acting. But when AI starts acting, and if AI fails, there is a huge challenge. The issue is that, what is today's AI? AI is essentially correlation. We are learning correlation between input and output in whatever way. Even if you see you're getting a distribution, from that distribution picking up samples, these are all basis of correlations. Okay. So if you see that a correlation is sales and shaved heads showing similar curve, if I took a correlation coefficient, it would be highly matching the two. But is it correct? We found a correlation in the data. Everyone take a razor. You cannot take such a decision. Okay. So therefore, it shows that correlation can lead to absurd results. Okay. And if you see here, this is the foundational principles. Actually, if you see, we work with primarily physics is causation. We work with causal mechanism, that is T implies Y. Given T, Y is always true. It's logic. And all your physics principles or theorems that we prove, that's as per the causality. But when there is correlations, I have given two examples, what is called confounding. Confounders, something like this one, if I look at X, X implies T and X implies Y. If I now say that T and Y are correlated, I am ignoring the confounder which is X. And therefore, there may be absurd correlations, because if the confounder is not known, that X is not known and X is something else. Similarly, if we look into these sample selection basis, because the spurious is a correlation, if it is T and Y is related, conditional to S. If S is not true, then this correlation is spurious. Is it clear? But when we actually look at data per se and try to do this correlation, we are violating the causal principles. Since we are violating the causal principles, that what we say that LLMs are hallucinating. Why it's hallucinating? Because they are constructing stories based on association. Even actually your LLM can produce a statement like Santanu Chaudhury is director of IIT Delhi. Because in my whole CV, there is IIT Delhi, there is director. And there is a correlation, but there is a what is confounding factors. Those confounding factors are not explicitly modeled in that kind of correlation which LLMs are generating. Although today there are attempts and tricks and techniques to use it, but this is something we should be very, very careful with. So most ML methods are therefore can even fool us and is a problem. So if you see now applications, and you have already stated all of these: fault diagnosis, fault prediction, performance monitoring, intelligent control, design and synthesis. But for all of these, I think we have to look at robust technology. Technologies are today there, but robust because there are data drifts. I do not always know the explainability, therefore the trustability is a question, and domain and context is also important. And this actually what I stated in the first time when I talked about, there has to be human in the loop. Today the whole focus is shifting towards human-centered AI, not AI by replacing human. I think this is also from an Indian context is extremely important, and that gives us an opportunity for invention, innovation, and new generation of product development. So this can be in healthcare, this can be cars, maybe drones and other things. So therefore these ethical issues, that fairness, then transparency, all of these are extremely important, and that you can ensure possibly if you have human in a loop and you design in a human-centered fashion. Because otherwise there is unreliability, there can be actually, we have found that there are examples of how these AI decisions are biased against women, biased against income, biased against skin colors. Because that bias is in our data itself. Okay, if you see in this audience, if all are engineers, then very few are women here present. So if there is a statement that women are not engineers, AI will actually support that statement because numerically that's what is true. And that is something which is very, very dangerous. And that's because, again, correlation and not causation. And therefore, this trustability and other things we built into with a stronger AI model and possibly today with human in the loop. And today what are coming up, one is quantum computing and AI. India started a quantum mission, and this is possibly the next generation of AI. And edge computing is AI is coming down to chips at a smaller level elements, which is there everywhere. Your car has got about 100 processors, and AI is associated with almost each and every processor in some sense, in some function on the automobile that you drive. And long term is AGI development and societal adaptation to AI. Societal adaptation involves preparing the workforce and AI-driven economy, addressing ethical concerns, and creating regulatory frameworks to ensure benefits all sections of society while mitigating risks. I think this is what something our younger generation should be concerned with. And when we make policy and policymakers at the institutional level, at a commercial organization level, these are the points which are very, very important and critical to keep in mind. Thank you.